Hello students. So in the last class we looked into the concepts of calculating area of plane regions, where we also looked into the formula how do we calculate the area which is bounded between two different curves. We also worked out few examples. Now, in area of plane regions, there are several other problems which we can actually work out with, and today we will look into some more examples where just to make the concepts of this area of plane regions a bit clear. So, just as a recapitulation, we'll start with another example. So let us consider another example. So let's say example 1 for today, and this example says that find the whole area of the curve x y square equals to a square a minus x and the y axis. So here in this case, the curve is the given curve here is basically is this one, and we have to calculate the area between this curve and the whole of y axis. So this curve would more or less will look like something of this type. So it will look like this is x axis, this is this is x axis, and this is y axis, and then it would look somewhat of this type. So this is our y axis, and we have to calculate the area between this curve and the entire y axis. So between this curve and this entire y axis. So of course this curve is symmetric at the point along the x axis. So it's what we have to do, we have to calculate the area of this region up to y axis, and then we just multiply it by 2. So that will give us the area between this curve and the y axis. So there are certain properties we can write. So the equation of the curve is x y square equals to a square times a minus x, and first property is the curve is, and the first property is the curve is symmetric along or about x axis, and it contains even power of y. The curve passes through, what is the point that it is passing through? It is passing through a comma 0, and so these are the two properties of this curve. So then to calculate the area, so the required area is equal to 2 times area bounded between the curve and the upper half of x axis. So this is this area basically. So that's the area bounded between this curve and the upper half of x axis, and we can calculate this one in the following way. So in this case, since we are calculating from from 0 to infinity in a way, because y is varying from x is varying from actually 0 to infinity, because we are going along the x-axis, we are going along the y-axis. So the equation of y-axis is y-axis is x equals to 0, and here we have x will go until infinity. So we can write integral from 0 to infinity x dy, and this can be written as 2 times integral from 0 to infinity. X value can be calculated as a cube by a square plus y square, and from here we can write dy. Now from here this will reduce to 2a cube times 1 by a, and then here we will have tan inverse y by a, where y is running from 0 to infinity. Now when tan inverse is infinity, then this value will be pi by 2, and when tan inverse 0, then in that case the value will be 0. So we will have 1 by a tan inverse infinity, so that's pi by 2. So the value will be pi a square. So this is the required area that is being bounded between this curve. So we can write this point as a0. So between this curve and the origin, and to calculate that, we just have to calculate the upper half and multiply it by 2, because this curve is symmetric along the x-axis. So this is and another example where we calculated the area of a plane region bounded between two curves. We can consider another example. So to talk about another example, we start with let us say a curve like this. So example 2. So this says that show that the area between a square x square plus b square y square equals to 1, and b square x square plus a square y square equals to 1, where 0 less than a less than b is 4 by ab, tan inverse a by b. So here we have to be a little bit careful. So it's not that so first of all we have to see what kind of curve they are. So we can see clearly that if we divide both sides by a square by b square, a square b square, if we divide both sides by a square b square, then this will be x square by b square plus y square by a square equals to 1 by a square b square. And similarly this will be x square by a square plus y square by b square equals to 1 by a square b square. So then in that case it's basically an equation of an ellipse actually. So this is our equation of an ellipse, and we can actually write in fact we don't have to multiply anything. We can write x square by 1 by a square and y square by 1 by b square, and that will be sufficient. So we don't have to divide anything. So it's pretty much obvious that if we can write it as a square x square plus b square y square equals to 1, then from here it will be x square by 1 by a square plus y square by 1 by b square equals to 1. So this is basically this will basically be our how to say square of the length of the semi-major axis and square of the length of the semi-minor axis. Similarly we can write this one as so this is our another equation of another ellipse. Now we note that a is less than b. So since a is less than b, from here it implies that 1 by a is greater than 1 by b. So then in that case in the first case now we are ready to draw our area bounded between these two curves. So this is our x-axis, this is our y-axis, that's the origin. So if 1 by a is greater than 1 by b, then in that case this will act as the this will act as the length of a square of semi-major axis, and this will act as the semi-minor axis. So our first ellipse will look like this, and since 1 by a square is greater than 1 by b square, so this ellipse will be inverted. So something like this. So the area bounded between them is this much, and since they contain x square and y square, that means they are symmetrical in a way. So it basically means that we have to calculate the area of any one of these parts and then multiply it by 4. So we don't have to calculate the area of all these sections altogether. We just have to calculate the area of any one of these small sections, and then that will give a multiplied by 4, and then it will give the area, total area bounded by these two ellipses. So we can call it as A, B, C. So OABC, area of OABC will be the multiplied by 4 will be the area of the entire region. So to calculate that, we can calculate this point of intersection, and if we calculate that point of intersection, so what we basically do, we substitute the value of x square from here to here, and we calculate the value of y, and similarly we substitute the value of y, then we get the value of x. So that means the point of intersection, so we get first point of intersection. So we get solving the two ellipse equation, we get one point of intersection as 1 by square root of a square plus b square and 1 by square root of a square plus b square. So these are the two point of intersection. These are the one point of intersection of these two ellipses. Similarly, we will get the point of intersection of this point, point of intersection of this point, and point of intersection of this point. And it will surely will give you, if you solve these two equations, it will surely give you the 4 different point of intersection, because once you are substituting the value of x here, then in that case you are getting the 2 roots of y, then 2 roots of y, that means you are getting 2 values of y, positive and negative. Similarly, for each value of y, then we will get 2 values of x, and then we have basically 4 combinations. So x and y both positive, x is negative, y is positive, then x and y both negative, and then x is negative, y is positive. So we will basically get 4 different types of combination here. That means 4 different types of point of intersection. All right. So we are just focused in this first quadrant, because we will multiply the area of the first quadrant by 4. Okay. So now that we have the point of intersection, we will write now the required area is equals to 4 times area of I have named it OABC, or so let me say it OABC O. So that's the area, and area of OABCO is basically 4 times area of if we call this point of intersection as B, if we call this point of intersection, let's say B, then in that case it will be so then in that case it will be area, let's say, of this curve and then this curve. So suppose this point is P, so I'm calling this point as P. So that means we are basically taking the area, the area of the entire region as the area of 2 different area bounded by these 2 curves, because this is the first curve and then this is the second curve. So that means we will integrate first from here to here and then here to here. So 2 x points. So that means we will get basically area of what is that? Area of OPBC. So OPBC plus area of PAB, OA BC, and then area of PAB. So, area of PAB, right. And for area of PAB, we have to, now we will calculate the area individually. So, for area of PAB, here this is the part of, so PAB is basically this one here, and this is the part of our inverted ellipse, and from here we have to calculate the value of y actually. So, if we calculate the value of y, then that will be, so for the area of PAB, the limits are given in the equation, limits are in the given equation. For area of PAB, limits are in the given equation from, so what are the limits? So, the limits are from this point to this point. That means this point is basically A, and this point is basically OP is basically A1 by A square plus B square. So, from OP to PA, right. So, from here to here and then here to here. So, the limit will be from OM to OC. So, this one is basically OP to OA. So, the limits are basically OP to OA, and OP is basically 1 by square root of A square plus B square, and OA is basically our A, and from here we can solve, and from here we can solve y. So, y is basically 1 by B is 1 minus A square x square. So, this is our y actually. So, now that we have y and we have our limits, so we can calculate the area of the region PAB. So, the area of the region PAB is basically integral from A square 1 by A square plus B square to A y dx. So, here we will have 1 by A square plus B square to A, and our y is this one, one minus A square x square dx. And similarly, the area of this region, similarly we will calculate the area of this region by integrating from 0 to 1 by A square plus B square, and then we will take the curve y from here. And now we have to find the integration of this thing here. So, we have to calculate the integral. So, this is pretty straightforward. So, we will take out A square from here. So, then it will be, if I take A square from there, then it will be integral 1 by square root of A square plus B square to A, and it will be 1 by A square minus x square, and then we will use the known formula of integral calculus, and if we integrate this, then this will actually reduce to something called then this will actually reduce to I don't know, the first part will reduce to sine in x times A square 1 by A square minus x square by A plus sine inverse x by 1 by A. So, this can be evaluated very easily, and similarly we can evaluate the area of this part as I showed you, that we have to now integrate from the origin to this point, and this point is 1 by A square plus B square, and then we will use this curve. So, the value will come from here. and in this case, in this case it is b square x square and then a square y square. So this is 1 by b square x square, and we will divide it by a, and sorry, so this one is b square x square and we have divided by a, so this is b by a, and this here is b square. So ultimately we will integrate with respect to x here, and then that will give us the required value of the integral, and similarly we will integrate this part, and that will give us the area of this part, and then we will sum them. So then it will give the area of the whole ellipse of this section, and then we will multiply by 4. So when we multiply by 4, that will be the required area of the whole region bounded by the ellipse. So the required area would be 4 times area of PAB plus, what was that, another one was area of OPBC, area of OPBC, and that will give us actually 4 times. So this will come out to be 1 by AB tan inverse A by B. So it's a bit lengthy example, but I'm pretty sure you got the idea what I was trying to say. So this is another way to calculate the area of the region bounded by two plane curves. So here in this case the two curves were ellipse, and you just have to always remember that in these type of examples you always have to draw the figure first. So if you can be able to draw the figure correctly, then first you have to notice where are they intersecting. If they are intersecting, then calculate the point of intersection, or at first you can solve them and then you'll get the point of intersection, and once you get the point of intersection, you sort of can draw the figure, and if you draw the figure, then you'll be able to see that whether you need to calculate the area only above the one curve, or you have to involve both the curves, and if you are involving both the curves, then you have to guess the limits correctly like we did in this case, and once you have the limits correctly, then calculating the area would be pretty much straightforward. All right, so next point we have in agenda is sectorial area. So sectorial area, this is motivated from a polar coordinate system. So sectorial area means if r equals to f theta be the equation of a curve in a polar coordinate system, in a polar coordinate system, then the area of the sector enclosed by the curve and the two radial vectors or two radii, sometimes they are also called as radial vectors, theta equals to alpha and theta equals to beta, is 1 by 2 integral from alpha to beta r square d theta. We will not go into the proof, but what we mean is, so suppose this is our x axis in a way. So this is our x axis, and suppose this is a given curve. Now this point here is the point P, and this is our point A, and that's our B. So this angle XOA is basically angle alpha, and XOB is basically our angle beta. So, the sectorial area means the area bounded between OA and OB and this curve. So, this area and this radii vector, this radii vector and the curve. So, that particular area. So, this area is basically called as the sectorial area, and it is given by 1 by 2 integral from alpha to beta r square d theta. This is very useful when a curve is given in the polar coordinate system. We will see that what do we mean by it. So, if a curve is given in a polar coordinate system, we can calculate the sectorial area using this formula. So, let us see an example. So, let us say we have find the area of the cardioid r equals to a times 1 minus cos theta. So, the curve, first of all, if we draw the a cardioid. So, I am pretty sure you may have seen the figure for the cardioid before. So, it looks something like this. All right. So, that is the origin. Let us say this is the point A, and that is how it looks like, and it is symmetrical. The curve is symmetrical about the initial line. So, the initial line is basically theta equals to 0. So, if theta is 0, then in that case we have cos 0 as 1, and this one will be 1 minus 1 0. So, r is also 0. So, that means this is our initial line where theta is 0 and the curve is actually symmetrical. So, the required area will then be just theta from 0 to pi, because it is symmetrical along this initial line. So, we just multiply it by 2, and that will give us the area of this entire cardioid. So, the required area is equal to integral from 0 to pi r square d theta, and since the formula is 1 by 2, we write 1 by 2, and since the required area is 2 times of the area of any one of these sections. So, we have to also write multiplied by 2 here. So, then in that case this 2 and this 2 will get cancelled, and we will have 0 to pi r square d theta. Now, r is a times 1 minus cos theta whole square. So, here we will have a square, here we will have a square d theta. So, this will turn out to be integral from 0 to pi 1 minus 2 cos theta plus cos square theta d theta. Now, I can write 1 by 2 here, and then this will reduce to 1 minus 2 cos theta plus 1 plus cos 2 theta by 2. Now, evaluating this integral is fairly easy. I am pretty sure you can be able to evaluate. So, this will become theta, this will become 2 minus 2 sin theta, this will become theta by 2 plus 1 by 2 times integral of this one will be sin 2 theta by 2, and then you substitute the value of theta. So, ultimately you will be able to obtain a square times 3 pi by 2. So, this is basically 3 a square pi by 2. So, that is the area bounded by this cardioid between in this region actually. So, you see instead of converting this into a Cartesian coordinate system and then trying to draw this curve and also finding out the limits and all, we just had to remember the shape of this curve, and we from the shape we can see that the curve is symmetrical about the initial line, and then we can calculate the area or the sectorial area in this sense by just writing the limit 0 to pi and then multiplying it by 2, so that we'll have the entire area, and then you just do some simple calculation and that will give you the required answer. So this is a very interesting example where we actually didn't have to take help of the Cartesian coordinate system. We can consider another example. So let's see. So find the area of the curve, find the area of the curve r square equals to a square cos 2 theta. So the value of theta equals to plus minus pi by 4 will make r equals to 0. So for theta equals to minus pi by 4 it will be 0, r will be 0, and theta equals to plus pi by 4 r will be 0. So the curve is symmetrical about the initial line, and the required area, then the required area of the curve is equals to 4 times, because this curve is will look like something of this type. So this is our initial line, so that's the point A. Let's say this is point B, this is point, and this is point A, this is point B. So we are basically calculating this area and then we are multiplying it by 4. So 4 times integral from pi 0 to pi by 4 r square d theta, and then here we will have 1 by 2. So this is basically 2 times integral from 0 to pi by 4 r square is a square cos 2 theta d theta, and then this one is 2 times, if we integrate then this will be a square and then sin 2 theta 0 to pi by 4, and then this will be 2 a square sin pi by 2 by 2. So that means this will be ultimately a square. Yes. So the required area of this this is also called as a Lemniscate of Bernoulli, and the curve actually looks like this. So in order to calculate the area, we have to see for what value of theta this is becoming how to say 0, r becoming 0, and that will actually give us the limit from where to where we have to integrate, and the area of the entire curve will be given by 4 times the area of these small sections. So 4 times the area of the entire sorry, not entire, of this region is 4 times this region, and then the area of the entire Lemniscate of Bernoulli will be a square. So this is another way where you can calculate the area of a curve which is given in terms of polar coordinates. So we will stop here for today, and we will continue with our further examples in our next lecture.